So today is lecture 3, and today's title is regular semisimple elements. So we've actually already seen regular semisimple elements. So let me tell you the definition, and then you'll recognize that we've seen it. So an element inside G. So G, maybe at the end G will change, but yeah. So G for G SL2FP, kind of as usual, is regular semisimple if it has distinct eigenvalues. So actually this also works if you change FP to any other field. Distinct definition. In fact, for SLN, GLN, this is also the same definition. Yeah, so maybe in general, this is the same definition for the correct interpretation of distinct eigenvalues. So let me just recall that on Tuesday, we saw that if G has distinct eigenvalues, then there are two families of such elements. Oh, so actually, so another thing is, I'll call this set of regular semisimple elements inside G. I'll write this as GRSS. And then later on, we'll also have the complement of this. So stuff in G that's not in regular semisimple. And then an N will appear before the RSS, and N stands for not. Yeah. Diagonalizable. It's automatically diagonalizable in over the algebraic closure. Oh. Oh my God, I'm having some. Okay. So so here are the two classes. So the first class is that G is conjugate to A inverse, where A is inside FP psi. And so and this was our T. And the second, and this was the case where the eigenvalues are inside FP. And then we had another case, the case when the eigenvalues weren't inside FP. And I wrote before that it's conjugate to something, again, diagonal, but now the diagonal things are inside FP squared. And so, yeah, so they are diagonalizable in this sense, as was asked. However, they won't literally look like this diagonal thing inside my current presentation of SL2FP. So what will they look like? So this was on the additional problems of was handed out on Tuesday. Is that the other choice is that it's conjugate to something that looks like A, B delta A, where recall this delta was a square, was an element inside FP whose square root was not in FP. And so we're allowed to take any A, B inside FP here. And such a thing, okay, so what what was written on the additional problem sets is that there's a map from all things of the form A plus B squared of delta to a matrix that looks like this. This is a group homomorphism, and this defines for us an embedding from our T prime into our SL2FP. So for this, see the additional exercises. Okay, so I want to say, okay, I see some squinting, so let me say a little bit more about this. So this may feel a little bit uncomfortable, but I claim to you that this is something that you've seen before. So inside SL2, okay, this is a bad place to write it. Inside SL2R, first, I claim that there's a way to write the norm 1 elements inside C into SL2R. And how does this go? This goes, you take A plus BI, and you send it to A, B, minus B, and A. This is your cosine, sine, minus sine, cosine. The rotation matrices inside SL2R. So this T prime is like a rotation matrices inside SL2FP. Yeah, please do not be alarmed by this. This is just something that you've seen before in a different guise. And the proposition that we had last time at the end of last class is that for an element G inside the regular semi-simple locus, you can actually easily calculate what the character of our RT G theta and our RT prime G theta are. And remember, we had this like two different behaviors based on whether you're on T or on T prime. And so let me write down what the statement was. So it says that the character of RT G theta evaluated at this G is equal to theta of A plus theta of A inverse if G is conjugate to this matrix here. And so this is something living inside T, and it's 0 in the other case. So in this second case, if this is conjugate to, maybe I write, so on the additional exercises, this map was called D prime, and it's called D prime because like, this is the diagonals and D stands for diagonal, and this is T prime, so this is diagonal prime. This is D prime of zeta for sub zeta inside the norm 1 elements, which I denote by P plus 1, mu P plus 1. Okay. And the second statement was that chi of RT prime G theta evaluated at G is equal to, and you have the opposite situation. It's going to be 0 if G is conjugate to A inverse inside T, and it's going to be theta of zeta plus theta of zeta inverse if G is conjugate to D prime of zeta, which is living inside my T prime. But maybe I want to put this uniformly, maybe like right like this. So this was on our character table. Our character table had a bunch of representations like this. And then at some point there was an RT G theta. At some other point there was an RT prime G theta. And then at some point there were stuff on T, stuff on T prime. And then this result says that you have theta inverse here. You have a 0 here. Over here you have a 0, and then you have a theta plus theta inverse here. So if you remember from the character table, this is not actually correct. We didn't have a theta plus theta inverse. We had a minus theta plus theta inverse. And this is an artifact of the fact that this thing is not actually a representation. This is minus a representation. So you can just formally multiply everything by -1. Okay, but this won't play a role today, but it's just yeah. So know that there is no contradiction. Okay, before I prove this, actually I'm only going to prove B, but before I prove this, are there any questions? Yes.
Theta over there is interpreted as a character of FP cross.
Yeah, theta is a character of whatever I put down here.
And on the right hand side?
So it's the same one. So this theta is the same as this one. Yeah. So T is like A inverse. So it is the same as FP cross. And then over here, theta is my a character on T prime. So I'm not changing the notation based on like these two thetas are not the same. The theta is always relative to what I put in the subscript here. But this brings up a good point. I mean, if you try, like, how would you try to evaluate something on FP star on something that looks like this? You cannot do it. And so then the character is 0. This is not a proof. Okay, so the proof of B relies on 2 facts that I stated yesterday. And let me remind you of these 2 facts. The first fact is a serious fact, in the sense that it's difficult to prove. And the second fact is a calculation. So this is the first fact. It says that if you look at this, this is something that acts on X, right? And I told you whenever something acts on X, it's going to act on this vector space. And action on the vector space, that's an endomorphism. That's an automorphism. It's a square matrix. So you're allowed to take trace of a square matrix. And so that's what this expression means. Some of the diagonal entries of what are the matrix representing the action of this element on this, right? And there's two pieces here exactly because X has a left action or a left multiplication action by G and a scaling action by mu p plus 1. And so what Deligne-Lusztig fixed point formula tells us is that this number is the same as the action of simply the identity on the fixed points of X by this G comma zeta. Okay, so where am I here? Okay. Great. So if we're to use this, the second thing we need to know is how to calculate this fixed point thing. How do we calculate this thing here? And so that's the second thing. And this is something you can calculate. So let me write out explicitly what this means. And this is a good exercise. I think it's on additional exercises. Is that right? The calculation of this. XY. This is all things inside our Drinfeld curve X, which remember was defined by xy to the p minus x to the py is equal to 1. So all things in here such that d on xy, now also scaled by zeta, is equal to xy. So that's just by definition what this fixed point thing is. And what you can calculate is that this has p plus 1 things, points, if G is conjugate to d prime of zeta and is empty otherwise. Okay. And so the idea here is that if we want to calculate this, it's enough to calculate this. But to calculate this is much simpler because this thing is either a zero-dimensional thing consisting of p plus 1 points, or it's zero. There's nothing there at all. And if it's p plus 1 points, we saw already that the cohomology of something zero-dimensional is just the set of functions on that many those points. So it'll be a p plus 1 dimensional vector space. So let's see this in action now. Ready? Yeah. Okay. So let's go. So we start with this RTG theta at G. By definition, this is equal to the trace of what? Of G acting on the cohomology of X, the part where theta comes in, right? The theta eigenspace. So in general, there's a thing that says, like, if you have an action on some vector space, how do you pick out, for instance, the invariant subspace? Well, what you can do is apply a projection operator that says you average over the action, and it'll kill all the stuff that's non-trivial, and it'll only leave the fixed points. And so we're going to do an analog here, but now twist by theta. So by definition, this thing is the same as taking an average over all zeta inside T prime of what? Of the trace of G comma zeta acting on the cohomology of this, okay? But I want to pick out the theta part. So I need to make sure that my theta is always going to be, so my zeta is always going to be acting by multiplication here. And so that's the definition. So this is a standard kind of thing in representation theory. This is called some kind of projection. You can take it as definition and you can verify it for yourself later. Okay. So now we're kind of in good shape because this piece here looks like what I can apply 1 to. So let's apply 1. So this is by 1. what is this going to be? This is going to be, oh, sorry. What does it mean to divide by a group? This is equal to this thing here. And now I'm going to replace this thing by the Deligne-Lusztig fixed point formula, which is trace of 1, 1 on the cohomology of the fixed points, multiplied by theta of zeta. And now we can apply 2. 2 tells me that this thing is 0 most of the time. The only time it's going to be non-zero is when G and zeta coincide. Okay, so now a comment here is if G is conjugate to D prime of zeta, and note, recall, or exercise, whichever one you want to call this, that this is conjugate to zeta inverse. So actually this is picking out 2 points. It's going to pick out for me a zeta and also a zeta inverse. So if I am in this situation that my G, which was fixed at the beginning, is equal to one of these 2 things, then I know that the cohomology of this fixed point thing is equal to the cohomology of P plus 1 points. Okay. And what is the cohomology of P plus 1 points? This is the space of functions on my P plus 1 points to C. This is a P plus 1 dimensional vector space over C. Okay. Okay, so that means that what I'm getting over here is I'm getting 1 over this, this number stays the same. Now I'm only picking out zeta and zeta inverse, the zeta and zeta inverse corresponding to my G here. And I'm going to be getting the trace of the identity acting on a P plus 1 dimensional thing multiplied by theta zeta plus theta of zeta inverse. So what's the trace of identity on P plus 1 dimensional vector space? So sum of 1, 1, 1, 1, 1, P plus 1 times. This is simply P plus 1. So this number here is equal to P plus 1. What's the size of T prime? P plus 1. So this thing and this thing disappear, and we are left with theta of zeta plus theta of zeta. Okay. So that's the end of the proof. Right? Hidden inside this is this vanishing statement already. Right? If G was actually conjugate to something like this, it has no chance of being conjugate to D prime of zeta. So already this entire thing was equal to 0, and you just get 0. There's no other work to do. So this fixed point argument is it's doing a lot all at once, right? The argument seems to only give me one equation, but I actually separated out that one equation into this thing because I think it's, yeah, it's somehow sometimes it's possible for math to be too condensed. So I uncondensed it to prove a point. Okay, so any questions? Yeah.
Yeah, sorry, could you just explain one more time how we get from the equality labeled 1 to the second equality?
Yes. So what I'm doing here is applying 2. So this is by the second fact. That fact tells me that this thing is only non-empty if this condition holds. So if this thing is empty, there's no vector. This is a 0 vector space. So we really only care about this when this is non-empty. And when it's non-empty, it's automatically just P plus 1 points. And so And so it leaves only these two contributions.
I guess I'm wondering what happens to the theta inverse term on the right in number 1 going to 2.
So this thing is non-zero if I'm conjugate to d prime of zeta or d prime of zeta inverse. So I'm plugging in zeta or zeta inverse into here.
Oh, okay.
Yeah. Other questions? So here's a good exercise. And certainly I can write this up after lecture, and so it's very clear what all the random exercises I've assigned during lecture are. And the exercise is to prove A using this fixed point method. In other words, you'll have to calculate the analog of 2 in the case that x is not the Drinfeld curve, but this G mod U, this finite set of points. So that's the first thing. But actually, you know how to prove A by hand too. And in fact, if you did problem 1 on the exercises, you already know the top statement. And so it's really the second statement, this vanishing statement, that you'd have to see in order to get the full proposition. Okay. Any questions? So as I waved at last time, I think I ended lecture in the following way. I said, okay, well, we get these four entries inside the character table. And what I told you is that, okay, so I guess 2 entries per irreducible. And what it turns out to be is that magically, knowing the character of a representation, of an irreducible representation on these 2 entries, if it's equal to this, then it's got to be this representation. If it's equal to this, it's got to be this representation. So there's a characterization thing. It's saying that, I mean, you're given 2 representations, you don't need to know the entire character on every single element. You only need to know it on these places where the character formula simplifies into this really beautiful form, just being theta plus theta inverse in average. So that's the next theorem. And the proof of this theorem will take up the rest of the lecture. It's not a difficult proof, but I'm very happy with the proof. So I want to take some time to explain it. And then if there's time, I'll tell you. Yeah, it turns out there's a version of this theorem that's also true for determining supercuspidal representations, as in Jessica Vincent's talk Tuesday evening. And so if there's time, I will state that for you as well. Okay, so here's the theorem. So this theorem is originally due to Lusztig in 1977. For P, there's an assumption on P. And the more of this symbol, the larger the P. I'm assuming that's standard. And it's due to myself and my collaborator Masao Oi, and this is the person who also enjoys rock climbing. And this is slightly one less. Okay, so the proofs are very different. Actually, we didn't know about Lusztig's work at the time that we did this. And so what I will tell you about is our proof. And so here's the theorem. Assume that theta is not the same as theta inverse. So this rules out 2 cases. It rules out trivial and it rules out sine. And all the other ones are fine. Okay. Then RTG theta is the unique, irreducible, satisfying star So so I don't have to write this out again, I'll call this star and I'll call this double star. And RT prime G theta is the unique, irreducible, satisfying double star.
Are both of these like for p greater than some absolute constant?
Yes, yes, yes.
Okay.
So,
You just found you have a smaller constant.
oh, it's a smaller constant, yeah. I don't remember what Lusztig's constant was. Lusztig's constant is something like 2 to the size of the Wild group. And then ours is something like Wild group over 2. So it's much smaller. So in practice, in this particular case, SL2, for this one, you need P to be, I think, bigger than 9. And for this case, you need P to be bigger than 7. I'm aware 9 is not prime. But also like all of this stuff that, by the way, all of this stuff that I've talked about, it doesn't only work for FP, but you can put FQ there where Q is a power of P and everything works equally well. And so actually the condition here, it's not actually a condition on P, it's a condition on Q. And that might seem like similar things, but the point is that like you could have something be true for like 2 to the high power, even if it's, like a condition on P might mean that you're not ever allowed to take P equals 2. A condition on Q means that you could take something characteristic too, just some large extension of F2. So there is a difference between a condition on Q and a condition on P. So I'll keep it like this because it's closer to the truth. Even though we've only been doing FP here.
SLN?
What?
Is it a theorem on SLN? The general theorem?
The general theorem says that you take G to be the FQ points of a connected reductive group. And you take T to be any maximal torus inside here. And if this thing is irreducible, then it's determined by this. Yeah. So it's a general, yeah. And you'll see in the proof, I don't use anything about SL2. So like P bigger than 9, P bigger than 7, those are SL2. I mean, you just have to calculate what that thing is. Yeah. And that constant is it's in terms of two things, in terms of T and in terms of G. So there's some like root theoretic thing that you can write down about G, for example, and then you can write down what the like a bound for what P has to be from that. But that's not the bound that I will write down. I'll just write down the one that comes from the straight calculation.
Do you know if the one you get is anywhere close to sharp?
It is close to sharp. So, there's a kind of when the T is non-split, then you can get a lower bound than when the T is split. And when the T is non-split, then actually we check by hand all the Q's for which it failed and see whether it failed for a good reason or a bad reason. So sometimes it fails because there's no such representation, and so it's kind of vacuously true in some sense. And then there's some small Q for which some accidents can happen, but I think basically everything is fine. Like maybe at worst Q equals 2 is bad or Q equals 3 is bad.
For general?
Yeah, for general, yeah.
Okay.
Yeah, and we just check for each case. Yeah.
For general G.
For general G, at least for Coxeter T, we can, basically the worst is like, sometimes okay, here's an example. For G2, I think we have to check Q equals 2, 3, and 5. And then so we just do this by hand, using some other trickery. But essentially there's actually no condition. So essentially, yeah, so I'd have to look to get like the complete finite list of all no condition things, but this is something that you can, these tori are characterized and you can actually do these calculations by hand, yeah, or using a computer. Okay, so let's do this. Okay, So what is our task? Our task is to do the following thing. Oh no, I erased star and double star. Okay, everyone remembers, correct? Okay. Okay, so let pi be an irrep of G. And what's the condition on, what do I have to say? I have to say, if pi is an irrep that either satisfies star or double star, then it's the same as RTG theta, right? That's the task. So such that the character of pi on the regular semi-simple part is equal to the character of one of these two things. So I'm going to denote it by the following thing. I'm going to put a big dot here to mean that either it's t or t prime. And so the proof is uniform in both of these cases. Okay. Okay, so that's what do we want to show? So our task is to show that pi, so okay, I'm going to write this expression like 30 times in the next half hour, and it's a lot of strokes. So here I'm just gonna write this as R. And here I'll also abuse notation. I will just write pi for the character. So our task is to show that the inner product of pi and R is equal to 1, right? Because we had that theorem from Tuesday that if I have two irreducible representations, the inner product is either 1 if they're isomorphic or 0 if they're not isomorphic. So this is our task. So we'll have 3 claims. I just tell you that too, so you have a feeling of how far we've gotten. So claim 1 is a rephrasing of this thing. Claim 1 is, it is enough to show that this thing on the regular semi-simple part is not the same as minus this thing on the not regular semi-simple part. So I haven't told you what the regular semi-simple part of this inner product versus the not regular semi-simple part is. So let me tell you what this is. So by definition, if you remember, this inner product is equal to an average over all elements inside G of this number. So remember, we're taking characters of these things, times this number, bar. And just by definition. And what can I do to this sum? I can split the sum into the regular semi-simple part and the not regular semi-simple part. So this thing here is equal to G RSS, disjoint union, not RSS. Okay. Okay. Now, we are trying to show this thing equals to 1, right? But we know that since pi and r are assumed to be irreducible, either this number is 0 or it's equal to 1. So actually it's enough to just show it's not 0, right? Because then it'll be 1. So it's enough to show that pi r is not 0. But this thing, of course, is the same as pi r on the regular semi-simple part plus pi r on the not very irregular semi-simple part. And you move it over to the other side of this in non-equality, and you get this statement. Yeah. Okay. Here's claim 2. Claim 2 is it is enough to show that the absolute value, my watch says, relax reminder, stress seems high at the moment. Moment to breathe. Okay, so it is enough to show that this guy on the regular semi-simple part is bigger than half. Absolute value of this number. Okay. So in the first claim, in some sense, nothing happened. We just observed that some number is 0 or 1. We want to prove it's equal to 1, so we just said that's the same as proving it's not 0, right? But in claim 2, something happened. And let me explain what I mean by that. R is one of these representations. That's the known thing. We know what that representation is. We have a presentation for what it is. Pi is the mystery irreducible that we want to show is equal to our R, right? So over here, a priori, we're trying to show that something unknown paired with something known is equal to 1. And here, we still have the unknown and the known. But what claim 2 is saying is that actually, in order to prove this, it's enough to show some trait about the known thing. There is no more pi in this statement. Okay, so this means it's good because we have control over what this is. We can then isolate our attention to the known stuff. Okay. So how do we get rid of pi? We use Cauchy-Schwarz. As promised, yeah? So Cauchy-Schwarz inequality is like something like 200 years old. And the second line of Wikipedia says it's maybe the most important inequality in mathematics. And it's very general. And it says like, whenever you have a vector space with an inner product, if you take two vectors, v and w, you take this size, this is bounded above by whatever v was with itself and whatever w was with itself. So I feel when I was in undergrad, I felt like every class I took began with a proof of Cauchy-Schwarz. And I think this is basically the statement that cosine is not bigger than 1. Is that right? Roughly. Okay. So let's apply this. How are we going to apply this? We have inner products. And we have this, and we're not going to apply it to the regular semi-simple part. We're going to apply it to the not regular semi-simple part. So apply to this one, NRSS. And so what does this say? This says that my unknown thing with my known thing on the not regular semi-simple part is bounded above by pi, the unknown thing, not regular semi-simple part, times r, and the not regular semi-simple.
Square roots.
Yes, very important. So probably if the square root wasn't there, then something with the proof still works, but yes, square root is there, yes. Okay, so now what do I do? This means that this unknown thing can be bounded above by this unknown thing times this known thing. Okay, so now here's an observation. It's going to be sneaky. So what we know is that definitely this by definition, this thing is equal to this. I have already written this a few times. This is true for R, this is true for pi, this is true for any representation, just by definition. We know it by assumption pi and r are irreducible. Yeah. So that means that both of these things is equal to 1. So in particular, they're equal to each other. What was our assumption now? Our assumption is that pi and r are the same on the regular semi-simple part. So that means on the regular semi-simple part, this thing is equal to this thing. But now there's only one remaining term in the equation. Right? If these two things are equal and these two things are equal, therefore, these two things are equal. Well, what does that mean now? This term is this term. So that means that this product is simply the same as this term. Yeah.
Could you just repeat why that second quality is true?
The second equality is true because of this assumption. The two characters are the same exactly on this regular semi-simple locus. That's our assumption. So by assumption, these two things are true. They're true term by term. So a remark, knowing that these two things are equal is not the same as knowing that R is the same as pi on the not regular semi-simple pi, right? This is an averaging of a bunch of stuff. This is an averaging of a bunch of stuff. So it's just saying the average is the same. Okay, so now what we have is that this mysterious thing is less than or equal to this mysterious thing. And what I need to show you is that if I have this bigger than 1/2, then claim 1 is true, right? Because claim 1 says it's enough to show this not equality. So I'm going to show you that this bigger than half now implies this non-vanishing condition. So if RSS is bigger than half, then what do I know? Well, I know RR is equal to 1, right? And so this means that R on the not regular semi-simple part is less than 1/2, right? So I have to get to 1. But now this thing I just proved bounds my unknown thing. And on the other hand, 1/2 is going to be less than this number. How do I? Okay, having some inequality trouble. And this thing, again, by assumption, is equal to pi r RSS. So in total, the conclusion of this is that this thing here is strictly less than absolute value of this thing. But if this thing has some norm that's different than this thing, then surely it is the case that this thing is not the same as this thing. So that's the end of this claim. Yes.
Is the last one pi RSS?
Yeah, pi r RSS. Pi r. Yeah, I want to show that pi r, not regular semi-simple, is not the same as pi r, regular semi-simple.
And so how did you get from RR RSS to pi?
Yeah, so for the same reason as here. Which came from the assumption that pi and r are the same on the regular semi-simple part.
But over there it's pi and RR and.
Oh, I see. Yeah, good point. Good point. Okay. Yeah, it's again this. So for the same reason, even though it's not the same thing I wrote down, I have this pi is equal to r on the regular semi-simple part. Any questions? Yes.
Sorry, I'm still very confused because like it is like the inner product is still pretty different from the one on the other side. Like why does it still why does the top implies the equality?
Which one? What's the
Like why does like the equality on the regular the semi-simple locus implies I guess the part about the inequality of the oh never mind, sorry, I'm stupid. I realized.
Okay.
Yeah,
Sorry, you're not stupid, but I'm glad we had a ding. Yeah. You're good? Okay.
Yeah, we're good.
Other questions? Okay. And so that means now all our effort is to show that this inequality is true. Okay. So I should say at each point here, I have, okay, claim one is actually an if and only if, but claim two is not an if and only if. This is just a sufficient condition. It's not necessary. And so this is the sense in which I answered the question about like whether it's sharp. I mean, we may have lost some data here because I demanded that this is bigger than half, and it's certainly possible for two numbers like 1/2 I plus 1/2 is not 0, but they both have the same norm. Yeah. Okay, now I have to decide where to put claim 3. Let's put claim 3 here. Yeah, claim 3. This is natural. This is natural. And then I don't have to erase any part of the proof. So claim 3 is now this last statement. The R paired with itself is bigger than half. Okay, so let's write down what this thing is, right? R on the regular semi-simple stuff. What is this? This is 1 divided by G, just by definition of R of G multiplied by R of G bar. Yes. And the previous proposition that we proved today told us exactly what R of G bar is. Yes, it's this thing where it's a theta plus theta inverse, depending on whether your G was inside the T where you're allowed to evaluate theta on or not. So remember that these things here, so this thing here, what was this thing here? This was equal to the sum of theta plus theta inverse at G. And it was kind of, yeah, so this depended on whether G was inside T or G was inside T prime. And another way to say this is inside SL2, there's what's called a Weil group. And the Weil group for SL2 is just plus minus 1. So it's Z mod 2. And what that thing does, that thing actually acts on these characters. And it sends theta to theta inverse. And so that means that this expression could alternatively be expressed as theta W of G, as W varies over elements inside the Weil group. Yeah, and as I said, the Weil group is Z mod 2 for SL2. But now this expression doesn't capture that sometimes this number is 0, right? Sometimes this number is 0 and sometimes it's not 0. And when is it? It just depends on whether G can be conjugated into T or it can be conjugated into T prime. And so I'm going to write something a little bit funny here. I'm going to write down this notation here. And what this means, this is the definition of this thing here. This is the set of all elements inside G such that conjugating G lands you into T circle. And remember, T circle is always the one associated to theta. So it's whichever one that is. And so what this is picking up is that if G, like say theta came from T, then this thing is going to be empty if G was actually conjugating into T prime. And the same vice versa. So this is a condensing of the previous proposition I wrote down. And so, the only reason I write this is because I find it psychologically easier to expand this out once I have it in this form. So I don't have like multiple cases and I'm dealing with this. Okay, so this thing is now equal to 1 over the absolute value of G inside G regular semi-simple. And then I have stuff inside here times stuff inside here bar. Okay.
Can I just ask a question?
Yes.
question, if this RG is just theta plus theta of G plus theta inverse of G, right? It's not like this whole sum.
Yeah, this thing is theta plus theta inverse.
Right.
But it's only theta plus theta inverse if G conjugated into the thing that where you're allowed to evaluate T.
Yeah, but I'm just like.
This piece
Yeah.
is equal to this thing. This thing is, oh, sorry, I need to divide by T here. T, sorry. No, it's fine. So this, whatever this thing is, this has two elements inside it if you conjugate it into the correct torus, and 0 elements if you conjugate it into the wrong torus. If you conjugate it into the correct torus, the action of this funny thing is exactly setting theta to theta inverse. And so averaging over theta W is picking up theta and also theta inverse. Okay, now I make a jump that you will have to justify. So this is the exercise. It's a calculation. And it says that this thing actually simplifies to this here. Okay. Again, this just means I'm telling you what the, you know, this is justifying the equality. Yeah, so. Okay, so we have this, so take this for, yeah.
Is that WT or just W?
Yeah, that's a good question. So if you put WT here, it's the same, yeah, so we can put WT here, it's okay, yeah, I can do that, yeah. That's a good idea. Okay, so I have an averaging over the regular semi-simple part. Of course, that's the same as averaging over everything in T minus all the stuff in the not regular semi-simple part. So I'm gonna split this into, this is the sum over T inside T minus the sum over T inside the not regular semi-simple part. Right, so this sum is the same as this sum here. So I'm gonna write this out. When you sum over everything, that's the same as the inner product on the nose. And so that means that this thing is going to be equal to the same thing as the average over W in W circ. Now you can put like identity here, I think. No, yeah, identity here. Identity here is okay. Identity here is not okay. Maybe I put a T circ here. This thing is going to be equal to theta W minus theta W on the not regular part. Yeah.
Sorry, I have a question on the notation. So like the T here means like that union of like T and T prime, right? So what is W?
It's not union, it's either T or T prime.
Okay,
Yeah, it's whichever one came with theta.
right. But in either case, because you only define W dot G for like a element in G, so like what is W dot T dot in this case?
This one,
The one you just wrote.
this one.
Yeah.
Yeah, I just mean for an element inside the correct torus.
So would that be sort of like a union of those W dot and then T for any T?
Yeah, you can take it to mean union. It'll turn out they're all the same.
Interesting.
Okay, so I have this thing now. Okay, my assumption was that theta is not the same as theta inverse, right? And what this sum is doing is it's in our SL2 case giving us theta plus theta inverse. And we assume theta is not the same as theta inverse. So this thing is equal to 0 and this thing is equal to 1. So this gives me 1 minus theta W and reg, and RSS. Sometimes I put reg there, and that's because Here's some terminology. If you have an element inside a torus, it's semi-simple. And so for an element inside a torus to be regular semi-simple just means it's an element inside a torus that's regular. And so that's why accidentally sometimes I change the notation.
Caroline?
Yeah.
You were something over W, but you seem to have a W that survived into your final,
Oh, yeah, yes. Thank you. Okay, so what happened here? Let's go over what happened. I looked at the inside of the left-hand side of my inequality that I need to prove, and I expanded it out. And what I showed is that this thing here is the same as this thing here. Now, one, I cannot do anything more with one. However, this other part, this sum over this not regular semi-simple part, that's something that I can try to bound now. And how do I want to bound it? Well, I want this one minus stuff to be big, right? So I want this stuff to be small. So let's try to make it small. And we know a way to make this a sum over stuff small. And this is theta and theta w on the not regular semi-simple part. And how do we make this small? I know the absolute value of this by triangle inequality is less than or equal to if I move the absolute value inside. But what is something like this? This thing is 1 divided by t bullet multiplied by the sum over all t inside the not regular semi-simple part of theta to the w of t. Okay. And so I can apply triangle inequality one more time. Absolute value of this is going to be less than or equal to absolute value of this. Oh my gosh, apologies. There's a theta of t times theta w of t bar. So absolute value of this. But what's the absolute value of a character theta? It's just 1. So this thing is equal to 1. So that means that this whole thing is less than or equal to 1 divided by this thing multiplied by, well, how many of these am I getting? I'm getting the size of W of them. And times the size of this not regular semi-simple part. And we know what these numbers are, right? For us, what does this give us? Let's do the two cases, t and t prime. So for t, I get this number is 2 multiplied by not regular semi-simple. If I have A inverse, when are the eigenvalues not the same? They're not the same exactly when A is not equal to A inverse, which is the same as saying A is not plus or minus 1. So there's just 2 stuff in here. So 2 divided by, and for t, what was the size of t? That's p minus 1. And for t prime, what's the number that we get over here? The number that we get is 2 times 2 divided by p plus 1. Okay. And so when is it going to be that this number is going to be bigger than 1/2? Well, it's going to be when this other number is less than 1/2. So what we want is for this number to be less than 1/2. And so this gives a condition on p. Sorry, this part I find really tricky because you have to like move stuff from the bottom to the top across the inequality. So over here I have 4 divided by p minus 1. Might as well just write it as 4. And so in this case I have p minus 1 is bigger than 8, which is p is bigger than 9. So that's the p bigger than 9 that I had before. And over here I have P plus 1 is bigger than 8, and that means P is bigger than 7. And so that's a P bigger than 7 that I said before. And so that's the end of the proof. Okay, so I'll just say the theorem that I promised because we're out of time, is what Jessica said in her talk is that the depth zero representations of SL2QP come from RT prime G theta. Those are the cuspidal ones. Those compactly induced to an irreducible, and that thing must be supercuspidal, therefore. And so given that you have this kind of characterization of these representations, it's natural to ask whether you can also characterize supercuspidals. And so that is a theorem. You can also characterize supercuspidal representations of SL2QP using similar criteria. There's some, I mean, in general, the characters of supercuspidal representations is an extremely difficult and subtle subject. And so it's especially worthwhile if you can know that you can recognize the supercuspidal just by knowing the character values on a tiny locus. And the tiny locus is the analog of something regular semisimple. You have to be a little bit more careful and a little bit more strict in order to get a nice formula, but that's the idea. And the theorem is that you can also do this for supercuspidals. And this is also, there's a general statement. You take a connected reductive group over a p-adic field, where p-adic means a finite extension of QP or a finite extension of the Laurent series over FP. And under some conditions, you can do this kind of thing. And I should say the proof of this uses Jessica's result about exhaustion of supercuspidal representations. So I'll stop here. Yeah, thank you. Any questions?
Could you please remind me what we're supposed to do?
Oh, yes, of course, yeah. And please, I really am serious when I say that anytime you see me walking anywhere, you can just stop me and ask me more things. So this is how how it goes for SL2QP. So for the ones directly coming from RT prime G, and it looks like this. So inside SL2QP, there's an important subgroup called SL2ZP, which is the same definition as we've been seeing. It's 2x2 matrices with coefficients and whatever is here and a determinant 1. And an important thing that you can do with ZP is that, remember, ZP kind of looks, things in ZP look like A0 plus A1P plus A2P squared plus and so forth like this. And what you can do is you can send P to 0. And so it chops it off here. And so all you're left with is this A naught. This A naught is inside FP. So there's a natural surjection from SL2ZP to SL2FP. And this is our G, right? And so I can take my RT prime G theta, which is a representation of this group. But because I have a map from this other group now also acts on this, right? How does it act? It says, take an element inside here, you look at where it went over here, and you look at how that acted on this thing. So now I have a representation on SL2ZP. How do I get a representation on SL2QP? I take the space of locally constant functions satisfying some nice condition. And so that's this compact induction. So the supercuspidal reps here. So what I'm going to write down is not everything looks like this, but the depth 0 ones look like this. This is the compact induction from SL2ZP to SL2QP of this RT prime G theta, viewed now as a representation of SL2ZP via this map from SL2ZP to SL2FP. Yeah.
What's a cuspidal representation again? What's the definition?
Okay, definition of a cuspidal representation is a representation whose pairing with any RTG theta is equal to 0. So there is some history as to how the cuspidal representations on G became super cuspidal ones on over QP. I have no idea who decided to add super. Yeah, but the notion of cusp has same origin as the notion of cusp in modular forms. Yeah.
Yeah, I was just gonna ask where's the cusp?
There's no cusp here. Yeah,
Okay.
because there's no, yeah, but the cusps. I thought it was glued to the ground. The cusps are on the modular curve.
I guess where does the cuspidal name come from in this case? Does it?
Yeah, because of modular forms.
Okay.
Yeah, yes. So the connection is modular forms gives you an automorphic representation. Automorphic representation, depending on what kind of level structure you took. So this like N that has appeared, like gamma naught of N, like these kind of congruent subgroups. This N is capturing how supercuspidal various components of your automorphic representation can be. And so that's why it's cuspidal. Yeah.
How similar is the SL2 or the SL2QP proof and the SL2SP?
So it's basically it's a reduction to the FP case. And so what you prove is that the structure of the algebraic construction of representations of something like SL2QP has two components. It has a geometric component, which is the one from Drinfeld curve that we've been talking about, and it has an algebraic component, which is the positive depth part. And so the proof of something like this goes like, if you know some comparison, then you first show that the positive depth part is coming from the same data. Then you say, okay, it's coming from that data plus something with the depth 0 things that satisfies this kind of condition, that it's a representation satisfying double star. Then you use a theorem like this to say, oh, well, now I know which representation it is. Yeah. Yes.
In general, do you know what's like the distribution between the regular semisimple and the non-regular semisimple?
Yeah, that's a good question. So this is actually quite a subtle thing. Is how many, so the question is how many regular semisimple elements are there relative to the number of not regular semisimple elements? And over the algebraic closure, they're like 0% will be regular semisimple, not regular semisimple. So this is a locus that's growing bigger and bigger as your Q increases. However, there's a rationality issue is that we're not trying to do something over FP bar. We're really trying to do something over FQ. It's a finite problem. And the rationality constraints are very important in improving this kind of thing. So you'll notice if you took the limit as Q goes to infinity, this number will go to 0. And so that means that the size of this thing is actually, it's not just 1/2, it's like, it's getting bigger and bigger as Q gets larger and larger. But since we're caring about this finite field thing, then one has to be careful. And this is where conditions about Q arise. And somehow you know the trend, but you're interested in starting behavior. Other questions? Okay, please. Oh, yeah.
So is there a bound on Q for the QT?
So sometimes the answer is yes, and sometimes the answer is no. And it's also a subtle thing because of rationality questions. So for depth 0, there is a bound on Q, and it's the same bound as in the finite field case. If you're positive depth, then you have to be a little bit more careful. But morally, it's also kind of coming from the depth 0 component. Good questions, everyone.